Hello everyone, my name is Andrew, and this week I'll be your lab instructor for Lab 10. Today we'll be talking about algorithm families and dynamic programming. But before we begin, let's look at a few announcements. So Lab 9 is due this Friday, and Lab 10 will be due the Friday after that, or April 17th. This week's lab will have an autograder portion and a quiz, as well as an exit survey, which we'll be posting a link to on Piazza as soon as possible, so keep an eye out for that. Project 4 has also been released, and that will be due on the 16th, or 2 Thursdays from now. And there's one thing that has changed, so this is no longer true. I'm actually re-recording this video just to redo this part. We will no longer have the exam at 8 a.m. Eastern Standard Time for everyone. So if you live in California, if you live in Hawaii, you don't have to take the exam at 5 a.m. or 2 a.m. because that's definitely not okay. Instead, we're going to give you 3 options for when you want to take the exam. So this is not confirmed yet, at least by the time I'm recording this video. So keep an eye on Piazza for any updates that are formally made. But essentially, we're going to give you options for when you can take the exam. I think the 4 time periods we're allowing are 8 a.m., 4 p.m., and midnight, all of these in Eastern Standard Time. So you can look at which of these time periods works best for you in your own time zone, and you can select the one that you want to use, or select the time period that you want to take the exam in when we send out a Google form later in the week. And then during the actual exam time, based on which group you're in, you'll be assigned an exam at your time period. So once again, this is a new update that just came in right now when I'm recording this video. So this may not be 100% accurate in the sense that some of the times may change, a few things might get updated, but as new updates come in, please keep an eye on Piazza. We're going to give you as much as we can, as many details as we can over the next few days as soon as we get them. So today we're going to talk about permutations and how to generate them for Project 4, algorithm families that can be used to solve different types of problems, and dynamic programming, which is a tool that we can use to solve problems that have overlapping subproblems. So the first thing we're going to talk about is generating permutations, which is something you'll be doing in Project 4, since you'll need to generate permutations of all paths that your drone can take so you can find the best possible path that gives you the lowest possible distance. Now, another example where generating permutations may be useful will be in the case of guessing a phone password. So in this case, if you've got your phone password, you can try out, let's say, all n factorial combinations of this password to see one that works. Now, in programming, storing all n factorial combinations in memory may be too expensive, especially for large values of n. So we'll need another algorithm that will allow us to enumerate through all possible permutations without requiring us to store everything in memory at once. And this is done using a searching algorithm, which we covered in the last lab. So for example, to do this, let's think of all permutations as being part of a tree. So if we want to generate all permutations of, let's say, 4 different possible colors, red, green, blue, and yellow, we can use this tree to illustrate all of these possible permutations. In this tree, each branch represents a unique sequence of something that we can have. So in this case, this leftmost branch, for example, represents the permutation blue, yellow, red, green, since that's a sequence of colors that appears down this branch. And similarly, this can be applied to all of the 23 other branches in this tree, each representing a unique permutation of these 4 possible colors. With this tree, we can do a depth-first search down each branch to enumerate through all permutations. And by doing so, we can ensure that we can visit all possible permutations by just storing the 4 possible colors in memory and not storing all 24 possible permutations in memory at once. So, why are we using a depth-first search rather than a breadth-first search? If you recall from the previous lab, a depth-first search visits each branch individually. So in this case, a depth-first search will look down one branch, then it'll look down another branch, and so on and so forth, visiting each branch individually. As a result, the maximum number of elements that you need to remember at any time during your search is equal to the number of colors or items that you can have in your permutation. In this case, we only have 4 colors, so the maximum number of colors we have to remember is 4. And this can be similarly applied to say that in a depth-first search, the maximum size of our stack, or the maximum number of elements we have to remember at any time, is equal to the number of elements that we have that we want to generate a permutation on. In this case, we have n elements, or n colors in the previous example, the most we have to memorize in our stack is on the order of n. However, if we recall, a breadth-first search instead visits elements in a level order. So going back to our tree example, a level order traversal essentially visits all elements on each level of this tree before it visits elements at a lower level. So when you're here, you would push these into your queue, and then when you're here, you would push these into your queue, and so on and so forth. Thus, for a level order traversal, the maximum number of colors you have to remember in your queue at any time is equal to the maximum number of colors that appear at any one level of this tree. In this case, our bottom level here contains n factorial items. In this case, with the 4 colors, there are 24 possible permutations. Thus, the queue will have to remember for this final level all 24 of these colors. Thus, we can say that the number of elements that need to be memorized at most for a breadth-first search is equal to the number of possible branches that we have. In this case, it's n factorial. So as a result, a breadth-first search is a lot more inefficient than a depth-first search when trying to generate permutations. Here's an example of the code we give you. This code does just what we covered in the previous slides. It does a depth-first search over all possible permutations that you can have that you want to generate. So this gemperms function takes in 2 parameters, a vector of items, which contains the items that you want to create a permutation of, as well as an integer infix, which stores the number of items that you want fixed in your items vector. And the gist of this function is as follows. Suppose, let's say you have a vector of items that has 1, 2, 3, 4, 5, and 6. And let's say you have an infix value that you passed in of 3. What gemperms is essentially doing is it generates all permutations that begin with 0, 1, 2, since you keep the first 3 elements fixed, while permuting the last 4 elements. So for example, passing in this items vector with an infix value of 3 will give you permutations such as 0, 1, 2, 4, 3, 5, 6, 0, 1, 2, 3, 5, 4, 6, and so on and so forth. So once again, here's a summary of how things work. Gemperms takes in a vector of items as well as an integer infixed, and it generates all permutations of the items vector where the first infixed elements are fixed. So for example, if we call gemperms on the sequence ACEBFGD with an infixed value of 3, gemperms will visit all 24 possible permutations that start with ACE. Now, what do we do after we generate a permutation? What if we need to do work on that permutation? Well, gemperms itself, even though it modifies the items vector since items is passed by reference, it reverts any changes to the vector before returns. Thus, the work that you have to do once you find a permutation must be implemented yourself. And the work here is done in this base case. Here, as we can see here, the base case specifies that infixed is equal to items.size. And when this is true, all items in the items vector are fixed. And that means that you have a full permutation. Thus, the work you do in this if statement is the work that you do to process the permutations that you generate. Now, we'll be covering this in more detail in the next few slides when we talk about how we can combine gemperms with branch and bound to help you find the lowest possible distance that you need to solve project 4. So branch and bound is essentially an optimization algorithm that can be used to find an optimal solution for a problem. Here's a pseudocode for branch and bound. Essentially, you'll be implementing a promising function that returns whether or not it's worth it to continue looking down a possible branch. If you know that a branch cannot give you an optimal solution, you can essentially ignore that branch and not look down any of the permutations that follow. If you find a solution that may work, you check it with the best solution you've seen so far and update it if it is better. Otherwise, you continue down the depth first search process we covered previously until you either find a possible solution or realize that the branch that you're looking down cannot give you a solution, and thus you can cut it out. We can use the branch and bound algorithm with our GenPerms code to solve the problem we want to solve in Project 4. So branch and bound involves a concept known as pruning. And pruning is essentially the process of removing all possible branches that you know can't give you an optimal solution. So in this case, suppose we know that all possible paths that begin with yellow cannot give you an optimal solution. If you know this information, you know that none of these combinations here can be the optimal solution, and thus you can completely ignore all possible permutations that begin with yellow. This is known as pruning, which essentially cuts out portions of your solution space once you realize that branches down that solution space cannot give you an optimal solution. In order to determine whether or not a branch is promising, you have to introduce bounds. And since the problem we're trying to solve in Project 4 is a minimization problem, where we're trying to minimize the total distance we need to connect all possible points, we can introduce something known as the upper bound and a lower bound to determine whether or not a branch is promising. The upper bound is the best solution that we've found so far. And the lower bound is an optimistic estimate for remaining solutions in this branch. That is, what is the lowest possible distance you can add to your path if you continue down the branch you're currently on. If the weight of the lower bound, that is the optimistic estimate, plus the total weight we've encountered so far on the current branch, if the sum of these two is already higher than the upper bound, that means at that point in the branch, no matter how low our solution can be, the solution that we get from continuing will always be worse off than the best solution we've found so far. And if that's the case, then we know that continuing down this branch is not worth it. So if the lower bound plus the current weight that you're currently on, the sum of those two, if the sum is less optimal than the current upper bound, then you know that the branch you're on will never give you the optimal solution, and you can prune this branch immediately in your program. Let's try to show this off with an illustration. Suppose you're running branch and bound on a minimization problem such as TSP, and at the current position in the branch, your current weight is 100. You know from running previous iterations that the best solution you found so far is, let's say, suppose 115. Now you want to ask, is it worth it to continue looking down this branch I'm currently on? To do this, we have to create an estimate to figure out what the best possible weight we can get if we continue down the branch is. So, to do this, we'll have to generate a lower bound or an optimistic estimate for what the best possible value we can get is. Suppose you run your promising function, which takes care of this, and you find that the lower bound is 105. This means that the best possible weight that you can get if you continue down looking down this branch would be a weight of 105. Notice here, and this is very important, the lower bound does not have to be an actual weight that you can get if you were to continue down this path. For example, these paths here, none of these solutions are equal to 105. That is, if you were to continue down this path, you'll never get a weight of exactly 105. But that doesn't matter when we're trying to estimate our lower bound. The only thing that matters in our lower bound estimation is that we have to guarantee that whatever value we get for our lower bound, it must be at least as good as all possible outcomes. That is, the number 105 in this example must be less than or equal to all the possible weights that we can get if we were to continue down the branch we're currently on. There are three situations that can happen if we do this. If our optimistic lower bound is less than the upper bound, we know that we should continue down this branch because we could get a solution that is better than the best solution we've found so far. In this first case here, let's say our original example where the current weight is 100 and the optimistic estimate is 105. The best we've seen so far is 115. since our optimistic estimate of 105 is less than the best so far of 115, there's a chance that we can get a solution that is less than 115, and therefore an improvement in our solution that we've seen so far. Suppose that one of these branches, this possible branch here, ends up giving us a weight of 107. In this case, we were able to find a solution that's better than the one we've seen so far, so our best so far after this iterative run would become 107 instead of 115. Now, there's another case that your optimistic estimate may be greater than the upper bound. And if that's the case, you know that you should not keep looking, because that means your optimistic estimate is already worse off than the best solution you found. So, for example, if our current weight is 100, the best we've seen so far is 115, and your promising function returns a lower bound of 125, what that means is that no matter what happens, if you continue down that branch, your total weight is going to end up higher than 125, which means that for your minimization problem, it's never going to go below 115, or your best solution. Thus, you should prune this branch entirely and not consider any of these possibilities, knowing that you're already going to be worse off. It is important to note, however, that just because you have an optimistic lower bound that is less than your upper bound or the best you've seen so far, that doesn't mean that you're guaranteed a better solution. It is entirely possible, as shown in this third case, that all the possible weights that you end up getting from continuing down that branch are all worse off than the best so far. But that's something that you don't know when you're trying to decide whether to prune a branch or not. All you know is that your optimistic estimate is the lowest possible solution that you could get. And as long as that lower bound is lower than the upper bound or the best you've seen so far, then you should continue looking, even if your continued search is doomed to fail. There are two invariants that must hold for a branch and bound algorithm to be valid. First, the upper bound, or the best solution you found so far, must be greater than or equal to the actual optimal solution. Second, the lower bound, or the optimistic estimation of what the best possible solution is if you were to continue down a branch, that value must be less than or equal to the optimal solution. If any of these invariants are broken, then the bounds could be invalid. That is, if you break these invariants, you could end up accidentally pruning out a correct optimal solution, or you could end up not finding the correct solution at all. Your bounds play an important role in determining the efficiency of your branch and bound algorithm. If your bounds are so tight to the point that they're incorrect, you may end up pruning out the correct solution or not end up finding a solution at all. But if your bounds are too loose, your promising function is going to return promising for pretty much every branch, and you're going to end up looking at branches that you shouldn't be considering at all, increasing your runtime and reducing the efficiency of your program. Thus, your bounds have to be tight enough so that it is perfect enough to give you an idea of which branches you should check, but also isn't overkill to the point that you're getting the wrong answer. And lastly, if the cost of computing your bounds already uses more time than the time saved from pruning, then your bounds are useless. The purpose of bounds in general is to save you time in determining which bounds you should continue looking down in order to find the optimal solution. If it already takes more time to calculate your bounds than it is just to check every branch, then there's really no point in calculating the bounds at all. So it's important for you to tune your bounds to make sure they're perfect enough to give you the efficiency you need to find the correct solution as fast as possible. So let's integrate this branch and bound idea with our gem_perms function. If you recall, the gem_perms function takes in a vector of items that stores the elements we want to permute, as well as a value in fixed that stores the number of elements we want fixed. Now we're adding pruning into this picture. As a result, not all branches are considered all the way to the very end. And because of this, this if statement now only runs if the current permutation has reached the end. That is, it is a permutation that has not been proven at all and is a possible candidate for the best possible solution that we've seen so far. Thus, in this if statement, you should implement what you should do to check if the current permutation has a weight that is less than the best weight you've seen so far. If this weight is indeed better, then you should update your best path as well as the best path weight that you currently have. We also have this if statement here that returns if promising returns false. This is where the pruning is done. The promising function here basically does work in calculating a lower bound and comparing it with the best solution we've seen so far. If we see that the lower bound is already worse than the best solution we've seen so far, then we just automatically return false, and thus the current branch we're on gets completely ignored and pruned out. Only if the branch is not pruned does this for loop run. Remember previously that this for loop is the actual for loop that does the permutations. So you're going to recursively call gen_perms for remaining elements that are not fixed, and the process is repeated where each branch is either checked to see if it's promising. If it's not, it gets pruned out. If it is promising, you continue looking until either it gets pruned or you reach this if statement base case, which you would check the current permutation to see if it's better than the best permutation that you've seen so far. So that's it for Project 4 material. But before we begin, let's look at several of the algorithm families you've seen so far in this class. So first we have the brute force algorithm, which is the most simple, obvious way to approach a problem. Most of the time, brute force is simply trying everything and choosing the best one. And the good thing about brute force is that it guarantees optimality, but it's also rather slow since you're trying everything, especially for input sizes that are large. The greedy algorithm is another algorithm that can be used to solve problems, and the greedy algorithm works by picking the next best option at every step. Greedy is efficient if it works, but it's not always guaranteed to be optimal. Recall the coin chains example mentioned in lecture, where suppose you want to create 14 cents worth of change using a 1-cent coin, a 7-cent coin, and a 10-cent coin. The greedy approach will just say, I'm just going to choose the largest coin possible to basically satisfy the 14 cents, and it's going to choose one 10-cent coin and 4 1-cent coins. But the optimal solution, if you want to minimize the number of coins, is in fact 2 7-cent coins, which is missed by the greedy algorithm. In general, the greedy algorithm only works if locally optimal decisions also lead to globally optimal solutions as well. Next, we have divide and conquer, which is an algorithm that splits a problem into many parts and combines the solutions to these subproblems to arrive at the final solution. One example of a divide and conquer algorithm is merge sort. To sort, let's say, a container of elements, you continuously split down the sizes of the inputs until you get little chunks of numbers that you can sort individually and merge back together at the very end. Backtracking and branch and bound are two other algorithms that we've covered in this class. Backtracking deals with constraint satisfaction problems. That is, it can be used to determine if a solution exists. Branch and bound, on the other hand, is an optimization problem, in that unlike backtracking, it doesn't just look at whether a solution exists, it also looks for the best, most optimal solution. Thus, the backtracking algorithm does not guarantee an optimal solution, since it only checks for if a solution exists, while on the other hand, branch and bound will always return the best solution. Both backtracking and branch and bound utilize pruning to determine whether or not a branch is worth continuing looking down. And lastly, we have dynamic programming. Dynamic programming is a tool that we can use to solve problems with overlapping subproblems to optimize time complexity. So let's get into more detail about the concept of dynamic programming. So dynamic programming is an approach that can help us solve problems with overlapping subproblems. Usually, dynamic programming involves recursion. Problems that can be used with dynamic programming often involve solving a problem with a larger input size using the solutions of problems with smaller input sizes. To show an example, let's consider the Fibonacci sequence. So the Fibonacci sequence is a sequence of numbers where each number is the sum of the previous two numbers before it. So here is an example of the Fibonacci sequence, and so on. Each number in the sequence is the sum of the two numbers that come before it. Now, if we want to write a program that can calculate the nth Fibonacci number, we can use recursion, since we know that, well, in order to get the nth Fibonacci number, all I have to do is sum up the n minus 1 and n minus 2, those two Fibonacci numbers, sum them together, and I get the nth Fibonacci number. So a naive Fibonacci solution would be like this. I essentially return the sum of Fibonacci, but with input sizes of n minus 1 and n minus 2. These two recursive calls deal with solving for each of these values that come before the value we want, and all we have to do is, after we finish these recursive calls, we add the solution together to get the nth Fibonacci number that we want. Now, what is an issue with this implementation? Well, let's say I want to find, let's say, the 50th Fibonacci number. So I call Fibonacci 50. What does Fibonacci 50 do? Well, Fibonacci 50 sees that in order to obtain the 50th Fibonacci number, we must sum up the 48th and 49th Fibonacci numbers. So Fibonacci 50 makes two recursive calls, one to Fibonacci 48 and one to Fibonacci 49. Now, what does Fibonacci 49 do? Well, Fibonacci 49 realizes that it has to make two recursive calls to Fibonacci 47 and Fibonacci 48 and sum up those two numbers to get the result. So 49 similarly calls 47 and similarly calls 48. We can also say that 48 calls 46 and also calls 47. And this process continues all the way to the very bottom until we reach the base case, as we see here. However, notice that we're duplicating work. When Fibonacci 50 calls Fibonacci 49, 49 ends up calling 48. But 50 also calls 48. Similarly, 48 calls 47, but 49 also calls 47. And similarly, this 48 call also ends up calling 47. So as we can see here, we're calling Fibonacci of 48, Fibonacci of 47 multiple times. But the result of calling Fibonacci 47 or 48 will always be the same. As a result, we end up doing a lot more work than we need to do, since we end up making a whole bunch of recursive calls that end up making even more recursive calls, which at the end, most of them aren't even necessary. So if we actually measure the time complexity of doing these recursive calls, we find that the time complexity of just recursively calling Fibonacci without doing anything else as exponential. So that's not good. So how can we use dynamic programming to fix a situation like this, where we have subproblems that are overlapping and they're called and being duplicated using these recursive calls? So how do we solve the problem of duplicated work? Now, one idea is to use the concept of top-down dynamic programming. Top-down dynamic programming is essentially the same as the naive solution, but with one caveat. Instead of just blindly calling recursive calls, before every recursive call, top-down dynamic programming will check to see if such a recursive call has been made already. So using our previous example, with a top-down approach, we would implement the Fibonacci function the same way. We return essentially the sum of Fibonacci n minus 1 and Fibonacci n minus 2. But with dynamic programming, before we call Fibonacci n minus 1 or n minus 2, we check to see if we've called that Fibonacci numbers with that input size before. So in this case, Fibonacci 50, for example, would usually call Fibonacci 49 and 48. But in this case, it checks to see if 49 and 48 have been called already. In this case, 49 and 48 have not been called yet. This is the first time 49 and 48 are being called, so the function behaves normally. We make a recursive call to 49 and 48. Now Fibonacci 49 calls 48 and 47, but with top-down dynamic programming, instead of blindly calling 48 and 47, we check to see if 49 and 48 have been seen before. In this case, we have called 48 before. So we don't have to make a recursive call to 48 to get the value of Fibonacci 48. So how do we know whether or not we've seen a value before? Well, we use something called a memo. And a memo is essentially a container that stores solutions to subproblems we've seen before. In this case, we have a one-dimensional problem where we want to find the Fibonacci number given an input size n. So one idea we can do is initialize a separate memo, in this case a vector, of size 51, where each index stores the nth Fibonacci number. So in this case, index, let's say 50, stores Fibonacci 50, index 49 stores Fibonacci 49, and so on and so forth. When we make a recursive call, we put the solution we get into this position here of the memo. And if we see that there's already a number in this index of the memo, then we know that we've called 49 before. We already have the solution for 49, so we can obtain the solution from this position in the memo vector. Similarly, when Fibonacci of 48 is called, we store the result in this memo the first time it is called, so that if Fibonacci 48 is ever needed again, we can look in our memo and see that 48 has been called before. We'll just take this value in O of one time, and instead of making the recursive call for 48 all over again. So here's the code for top-down dynamic programming. As you can see here, first we initialize a memo, in this case a vector that for each index I stores the ith Fibonacci number. We will use this memo to determine whether or not we've made a recursive call for a given input size before, and if we have, we'll retrieve the value from the memo instead of making a separate recursive call. Our Fibonacci sequence function continues as normal. However, this time, before we make recursive calls, we check to see if we've seen the value before. So this if statement here just resizes the vector so that it's the correct size, and it initializes every index of the vector to -1. Now what that happens is essentially the -1 serves as a flag that tells us that the number for that index has not yet been discovered and that a recursive call for that index has not yet been made. So for example, if let's say we look and we see that memo index 3 is -1, we know that we haven't made a recursive call with an input size of 3 yet. However, before we make the recursive calls, we then check our memo to see if we've seen the value before. So in this case, if the value at index n is not equal to -1, that means we must have made a recursive call before. So therefore, we don't have to make another recursive call since that will duplicate work. Instead, we'll take the value from that index and return that instead. Only if the index stores -1 do we know that that value has not been called yet. So then we can make the recursive call here. This is the same as before, but now this recursive call is only done once for each possible input size. The reason is after we find out what the result is, we end up storing the result in our memo to ensure that we don't have to call it again if we ever need that value. So, for example, if we call Fibonacci 3, we will figure out that the third Fibonacci number is 2, so we'll replace this -1 at index 3 with the number 2. Now, if we ever call Fibonacci 3 again, we can look in the memo and see that it's not -1, meaning that we've called Fibonacci 3 before, so we can just take whatever value is here, in this case 2, and return it. Similarly, if we wanted, let's say, index 53, you can see that this requires a lot more recursive calls to get the 53rd Fibonacci number. But with this method here, we can check to see if the 53rd index is filled with a number that's not -1. And if it isn't -1, we can take that value and use that in constant time. Since we're only calling each value once, each recursive call for each input size we're only calling once, the runtime drops from exponential to linear. Another approach is known as bottom-up dynamic programming. Unlike top-down dynamic programming, which starts at the very top with the large input size and makes recursive calls to smaller input sizes, each time checking to see if the solution has been found with the recursive call to that input size before, bottom-up dynamic programming starts from the bottom at the base case and builds up the solution one by one until the solution for the larger input size is found. In other words, for the Fibonacci example, instead of making recursive calls to 49 and 48, to calculate the 50th Fibonacci number using the bottom-up approach, we first calculate the 0th Fibonacci number, then the 1st, then the 2nd, then the 3rd, then the 4th, and so on and so forth. We store all these values in a memo, as before, but this time we are calculating all the values of all subproblems with a smaller input size than 50, and then using these subproblems to build up to the solution of the 50th Fibonacci number. Once again, we are only taking constant time to discover each Fibonacci number here, so the amount of time we require for the bottom-up approach is also linear. Let's take a look at the code for the bottom-up approach. Here's the solution for the bottom-up Fibonacci approach. Like with top-down, we initialize a memo that stores the solutions to smaller subproblems. But unlike top-down, where we start with the largest input size, in this case of n, with bottom-up, we start at the base case and build up the possible solutions to obtain the value we want. In this case, we declare a vector of size 51. Then we initialize our base case so that index 0 and index 1 store the 0th and 1st Fibonacci numbers. Then we do a for loop where we essentially calculate the next Fibonacci number over and over and over again from previously known Fibonacci numbers. So in this case, we sum up index 0, index 1 to get 1. Then we sum up 1 and 1 to get 2. Basically, we take the two numbers before it to determine what number goes to the next cell. And eventually, we'll stop when we finish this process and find out what the 50th Fibonacci number is. Once we've built up the solution to the very top and obtained what we want, we just return whatever value is at the position of the number that we need to calculate. Once again, since this is just a for loop where each loop builds on the previous solution using O of 1 time, the runtime of this overall algorithm is also linear. So here's a summary of the two dynamic programming approaches. The top-down approach is a recursive approach. It's very similar to the normal naive solution that just blindly calls recursive calls, but with top-down, before we make a recursive call, we always check to see if we've made that recursive call before. If we have, we return it by looking in the memo. Otherwise, we calculate the result, store the result in our memo, and then return the result. A real-life example of this would be, checking if there's food in your fridge. If someone asked you, is there milk in the fridge? Well, you'd have to open the fridge, dig through it to see if there's milk, and give the answer to the person who asked. But if another person asks 5 minutes later, is there milk in the fridge? The same question, and assuming that no one has opened the fridge before in that time, then you already know the answer to that question since you already looked for the milk before. So instead of opening the door, digging through everything again, and giving them the answer, you can just tell them the same answer you had before since you already did the work. This is the same with programs. Recursive calls take work. It's the same as opening up the fridge and digging through to see if something's in the fridge. So top-down dynamic programming saves that work by essentially using a memo, where the memo is essentially kind of like a sticky note where you stick on the door of a fridge that says, yes, there is milk in the fridge, so that if someone asks you, is there milk in the fridge, you can just look at that sticky note and give them the answer instead of going through and opening the fridge and digging through everything all over again. The bottom-up dynamic programming approach is another approach that we can use, and unlike top-down, bottom-up is iterative rather than recursive. The bottom-up approach starts with the base case and builds up the solution all the way to the value you want. So for the example of the Fibonacci numbers, to calculate the 50th Fibonacci number using a bottom-up approach, we use the base case and we use relationships with these numbers to build up the solution all the way to the 50th Fibonacci number. Once we reach the value we get, we can stop and return the value we are trying to compute. Now let's look at some dynamic programming questions. One common dynamic programming question is the positive subset sum problem. In this problem, you're given an array of numbers, and you're asked whether or not a subset of these numbers can be used to sum up to a target value. So for example, with this problem, we could ask, is there some subset of this list that sums up to exactly 104? Well, in this case, the answer is yes. You can take the numbers 9, 15, 36, and 44 to get a sum of 104. But we could also change the target value. What if we asked you with the same numbers, can we sum up to exactly 106? Well, in this case, the answer is no. There is no sum that can sum up to exactly 106. So how do we know whether or not the sum or the list numbers can sum up to a target number? So one way to do this would be to just brute force everything. We're going to try out all possible subsets and basically sum them up and see if any of them match the target value. But the time complexity of this is not so great. Note that there are 2 to the n possible subsets, since each number in your array can either be in or out of the subset you're currently considering. And for each subset, we have to do a summation, which takes approximately O of n time. So as a result, the time complexity of this brute force approach is O of n times 2 to the n. And that's definitely not feasible. So instead, let's use a dynamic programming approach to try to solve this problem with a lower runtime. So how do we do this using dynamic programming? Well, let's go back to the previous example. Our goal is to first determine a recurrence relation. That is, how can we write the solution for a larger input size in terms of the solutions to the same problem but with smaller input sizes? In this case, is there a way to use a solution for whether or not it's possible to sum up to 104, but with the smaller input size of 6, that is, only the first 6 numbers without the last 68? Can we use the solution for whether or not these 6 numbers can sum up to 104 to determine whether or not we're able to sum up to 104 using all 7 numbers? And the case here is that it is. Here's what you have to notice. Suppose I have only these 6 numbers to choose from to determine whether or not we are able to create a subset that sums up to 104. Notice here that the solution for this will allow you to easily determine whether or not the 7 numbers or all the numbers in this array will allow you to sum up to 104. And this is why. Suppose you know that this subset of 6 numbers can indeed sum up to 104. What does that tell you? Well, that tells you that if you were to include all 7 numbers, the solution must still be the same. It cannot change because you're already able to sum up to 104 using the first 6 numbers. Adding the 7th number doesn't really do anything. You can just ignore the 7th number and use the previous subset that you had to obtain 104. So if this were true, then by default, this must also be true. But what if this were false? If you instead knew that it's impossible to sum up to 104 with the first 6 numbers, does that give you an indication of whether or not you can solve it using the first 7 numbers? And the answer here is yes again. And the thing to note here is that if you cannot solve 104 using the original subset of 6 numbers, then in order for the 7 numbers to be true, then this 68 must be in the subset sum. Otherwise, if there's no way to obtain a sum of 104, even with adding the 68, then there is no possible way to sum to 104 using the 7 numbers. What does that mean? That means that in order for this to be true, if this first input size is false, then it must be possible for this initial subset to somehow be able to sum up to 104 minus 68, in this case 36. We can note here that if this smaller input size can sum up to 36, that means by default, adding 68 must allow it to sum up to 104, because all you have to do is use this subset of numbers to sum to 36, and then add 68 to your subset sub to get a sum of 104. On the other hand, if you know that this smaller input size cannot sum up to 36, then you know that it is impossible to sum up to 104 using the larger input size after you add the 68. Because you know that the only way to add to 104 with the addition of 68 into your array is to be able to sum to 36. If there's no way to sum to 36, then there's no way to add that 68 in any way to get a subset sum that equals 104. So now we can write our recurrence relation for this problem. First, we have the base cases. The base cases are essentially the cases that we can determine trivially without any computation. So for example, we know that if you have 0 elements, then it's possible to sum to 0. That's a given. If you have nothing, you can sum up to nothing. We also know that if you have 0 elements, that it's impossible to sum to any number that's other than 0. In other words, if you have no elements, you can't sum up to 1, or 2, or 3, because you have nothing to build on. But other than these base cases, now we have to write the recurrence relation for this problem. And as we mentioned previously, the recurrence relation is as follows. Given a given number of elements in your array, as well as a target value, which we'll call x, then the recurrence relation is first make a recursive call to the input size -1, that is all but the last element, and then we see whether or not it's able to sum up to the difference between the target number and the last number. This is similar to the example of the 104 minus 68. If this were true, then this must also be true. We also make a recursive call to the same recursive relation, but with the input size of k-1, or again, all but the last element, and x, or the same target value. This is like asking, can the first 6 numbers already sum up to 104? If either of these conditions are true, then we know that the overall condition for an input size of k and a target value of x must also be true as well. So as a result, we make these two recursive calls, we OR them to determine whether or not one of these is true, and if one of them is indeed true, then we use the result to determine whether or not this is true for the input size we want to look at. So now let's look at an example of the top-down approach for solving this problem. With a top-down approach, we just make the same recursive calls as we made before, but before every recursive call, we check to see if we've seen that recursive call before. In this problem, we're trying to solve whether or not it is possible to sum up to a sum of 9 using 4 numbers in this array. And for this drawing, note that the values of the sum and the number of elements in the array are flipped as parameters, so the sum in this case is the first instead of the second term. For this example, since this drawing was already made before, we're just going to treat it as if the numbers are flipped. So treat the first number as a sum and the second number as the number of elements you want to consider. But if we just make several recursive calls, this is what we end up getting, right? For each subset sum call, we check whether or not it's already possible to sum to the sum already using the last, all but the last element, and whether or not it's possible to sum to the difference between the last element and the sum and using the first k-1 elements. So we're going to make all these recursive calls like we usually do. However, with a top-down approach, our goal is to store the result of every recursive call whenever we see a recursive call that we've never seen before. And to do this, we will use a memo. For this problem, we can see that we have 2 variables that determine the input size. First, we have the number of elements in the array, in this case, this 4 here. Then we also have the sum that we want to sum up to. And both of these numbers determine the input size and contribute to a recursive call. So for example, we can't just look at one of these input sizes to determine whether or not we made a recursive call before. For example, if we've called subset sum of, let's say, 4, 1, that doesn't mean that it's the same as calling subset sum for 2. These are 2 very different recursive calls. So you need to keep track of both values to determine whether or not you've seen a recursive call before. So our memo this time will have to be 2-dimensional. Where one dimension is the number of items in your array that you're considering, and the second dimension is the target value you're trying to achieve. So for this case, we can use a 2D memo where the rows of the memo are the number of elements you want to consider in the array, so in this case 0, 1, 2, 3, and 4, and the columns represent the target sum that you're trying to sum up to. So in this case 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now each cell of this memo now stores the result of whether or not you've seen this recursive call before. In other words, whatever the result of subset sum 9, 3 is, or in this case 3, 9, using the previous notation of using the number of elements first and then the sum, whatever the result this is, we store it at index 3, 9 of our table. So this cell here. Similarly, when we make this recursive call, we check to see if we've seen the value before in our 2D memo. In this case, whatever the value is, we haven't seen it before, so we make a recursive call here and store it at position 3, 6 of our 2D memo. We can repeat the process. We ask ourselves, have we called subset sum on an input size of, or array size of 2 and a target sum of 6 yet? If we have, we look in the memo to see if we have. Otherwise, we store it in position 26 of our memo. Same thing with here. We look, see if we've called it yet, and if we haven't, we make a recursive call and store it in the correct cell. So we keep on doing this for all the recursive calls until we reach the base case. Now, why is this useful? Well, this is because that there are overlapping subproblems with this problem. If you can see here, this is an alternative diagram that shows the same recursive calls, but now this highlights the duplicate work that we may end up doing if we just recursively called everything. So in this case, with the problem we had before, we end up calling subset sum with an input size or array size of 1 and a target sum of 4 2 times. So if we were to just use recursion without a memo, we would make 2 recursive calls that do the same thing, therefore wasting time and computational resources. But with a memo, what would happen is that we would realize that with our first recursive call to 1, 4, so in this case 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, all the way up to 9, with the first recursive call to 1, 4, we would see that we haven't called the value before, and so we add it into our memo at position 1, 4. Once again, we're flipping the coordinates here just to be consistent with the previous notation that we had before, with k being before x. But when we make our second recursive call here, we look in the memo to see if we found the value before. In this case, since we know the solution for whether or not it's possible to sum up to 4 using one of the numbers in the array, then we can look in our memo, see that we've calculated this result before. So instead of making the recursive call itself, we just take the value from the memo and use it as the solution for our recursive call. So here's the code for the top-down approach. In this case, we declare a 2D memo. And I do want to mention that for here, we use an unordered map instead of a 2D vector. And the reason why we do that is, even though you can treat it as if it were a 2D vector, the issue is we have a bool that we want to keep track of in each cell. So each cell can either be a value of true or false, since those are the only 2 values that a Boolean can take. And since we want to initialize it to something that can determine whether or not we've seen the value before, we don't have access to like a -1 value like we did with integers. So it would be pretty difficult to initialize a table full to false, because you wouldn't know if a false value in the table actually meant that the solution for the subset sum problem for that input size is false, or whether or not we haven't made the recursive call for that input size yet, so we don't yet know what the value for that cell is. So instead of using a 2D memo, because the difficulty of creating a default value using just a bool, we use an ordered map by basically determining, hey, if this value is not in the unordered map, it hasn't been seen yet. So by doing this, all values of true and false we know must be valid actual solutions to recursive calls we made before. So now, instead of making these recursive calls blindly, before making these recursive calls, we first check to see if we've made the recursive calls before for the same input size. If we have, then we just simply return the value in that cell of the memo corresponding to the input size we're trying to use. If we haven't found the recursive call yet, then this if statement will not run, which will lead us to make the 2 recursive calls that we have to do. Now, before we return the answer, we then store the answer we get into our memo, so that if we ever need the same recursive call again in the future, we can look to see in the memo, yes, we've made a recursive call to this input size before, therefore we don't have to make it again since the answer is the same. We just take the value out of the corresponding location in the memo and return the value instead when we have a later call. So now let's look at the bottom-up approach to solving the same problem. Unlike the top-down approach, which starts at the top and makes recursive calls, checking to see if each recursive call has been seen before, the bottom-up approach starts from the very bottom at the base case and builds upwards to the input size we want. That is, it generates all possible solutions with the same problem with smaller input sizes and uses those solutions to help us build up the solution we want in order to get the input size that we want. So in this case, we start with the base case. Our first job is to fill out the cells in this table that can be determined trivially. So in this case, we know that 0, 0 is true. That's because if you have nothing, you're able to sum to nothing. We also know that you can't sum to anything other than 0 if you have no elements. So we know that 0, 1, 0, 2, 0, 3, all these values here in the first row, they're false. And lastly, we know that all these values in the first column must be true. And the reason is because even if you have 1, 2, 3, 4, 5 items, no matter how many items you have, if you're given a target sum of 0, then you can always sum to 0 by just taking the empty subset. So these are the cells that we know, whose values we know automatically at the start of the problem, and these are our base cases. Now our goal is to fill out this table, and we start with the cell here, 1, 1. So what value should go in this cell? Well, this cell represents whether or not it's possible to use the first item. In this case, I'll draw it out here where the first item is 1, the second item is 2, the third item is 5, and the fourth item is 3. Whether or not the first item can be used to sum up to a target sum of 1. Well, how do we know whether or not the first item can sum up to a target sum of 1? Well, we use the same recursive relation as before. To determine whether or not we can sum up to with a certain number of elements to sum to a certain target value, we check to see if either it's possible to sum up with all but the last element and sum up to the target already, or if we can use all but the last element to sum up to the target minus the last element. This is our recurrence relation. So we do the same thing here. We look at whether or not it's possible to sum up to k minus 1, well, sum to x using only k minus 1 elements. That is, whether or not it's possible to sum up to 1 using an input size of 0. And we also look at whether or not it is possible to sum up to the difference between the target value and the last element. In this case, the target value is 1, and the last element here is 1. So we do 1 minus 1 using only k minus 1 elements. In this case is 0. 1 minus 1 is 0. So once again, just to repeat, this value here was attained by looking at a target value x, which is the number we're looking at here, and or the last element, which is the last element in the array we're considering. So for row 1, the last element is 1. For row 2, the last element is 2, and so on and so forth. So these are the two recursive calls we need to make to determine whether or not 1, 1 is true or false. With the bottom-up approach, instead of making the recursive calls, we just look at the tables with the cells corresponding to these recursive calls. In other words, we look at cell 0, 0 and 0, 1 to determine what value should be here. Then we take the OR of these two values, since if any of these are true, then this must be true as well. In this case, it is possible to sum up to 0 already with 0, so we know that it is possible to sum up to 1 with 1 by just taking the first element. So this cell here is true. And we can repeat the process for the other cells in this table as well. So now let's look at the next cell. We want to see whether or not it is possible to sum up to a value of 2 using just the first element. And once again, the first element is 1, the second number is 2, the third element is 5, and the fourth element is 3 from this table here. Determine whether or not it is possible to sum up to 2 using an input size of 1. We make, again, two recursive calls. We look to see whether it's possible to sum to 2 already using an input size of 1 minus 1, in this case is 0. Then we also look to see whether or not it's possible to use the first 0 elements to sum up to the difference between 2 and the last element. The difference between 2 and the last element is 2 minus the last element, which is 1 for row 1. So the answer here is 2 minus 1, or 1. So we look at the values at cells 0, 2 and 0, 1, which are these two cells here. We take the OR of these values to determine whether or not it is possible to sum up to 2 using the first element. In this case, we can't, since these two values are both false. We also know that it's impossible to sum up to 2 using just one element in our array. We can continue the process and keep on filling out the table. In this case, let's look at this cell here. We want to see whether or not it's possible to sum up to 2 using the first two elements, where the elements once again are 1, 2, 5, and 3. Well, we know that in order to determine whether or not we're able to sum up to 2 using the first two elements, we need to determine whether or not it's possible to sum up to 2 using only one element, and whether or not it's possible to use only one element and sum to the difference between 2 and the last element. In this case, the last element is 2, since we're looking at two elements, and the second element is 2. So the difference between 2 and 2 is 0. So if any of these are true, then this must be true. So once again, we look at cells 1, 2, and 1, 0 of our memo. We take the OR of these values to determine whether or not it's possible to sum up to 2 using the first two numbers. So here's an exercise for you. We fill out the entire table with the exception of this last cell here. And we want to determine whether or not it is possible to sum up to 5 using the first 4 elements. In other words, all the elements we have is it possible to sum up to 5. So what is the recursive call we need to make? So we know that we want to determine whether or not it's possible to sum up to 5 using the first 4 elements. What are the two recursive calls we need to make? Well, once again, we need to first determine whether or not it's possible to use the first 3 elements to sum up to 5 already. And if this were true, this must also be true. And then we also need to determine whether or not it's possible to use the first 3 elements to sum up to the difference between 5 and the last element. Well, the last element here is 3. Since we're looking at the 4th row, we're looking at the 4th element, and the 4th element is 3. So the difference between 5 and 3 is 2. So we need to look at cells 3, 5, and 3, 2. We know that cell 3, 5 is true. We know that cell 3, 2 is also true. We take the OR of these values, and since true or true is equal to true, then we know that this cell must also be true and that it's possible to sum up to 5 using an input size of 4. So here is the same solution that we did before. So here's the code for the bottom-up solution. As you can see before, we start off with declaring a memo, since that's what we always do for a dynamic programming question. In this case, the memo's dimensions are determined by the two things that affect the input size, the target value we want to sum to, and the number of elements we want to consider in our array. Then we go through and loop through and build the table from the bottom up. We first start with the base case. We fill out the base case values first in our memo. Then we use the recursive relation that we've discovered for this problem to build the table up. In other words, in order to determine whether or not a cell in the table is true or false, we look at whether or not it's possible to use the first k-1 elements to sum to our target value already, and whether or not it's possible to sum to the difference between the target value and the last value in our array using the first k-1 elements. And if either of these values are true, then this must also be true. So that is why we take the OR of these two values to determine what value should go in this table. Then at the very end, we return the cell or the value at the cell of the input size we want. So in this case, we want to determine whether or not it's possible to obtain a target value using the first k elements that we want, or the k elements that we want. So we return the value at location, target, and num.size in our ultimate table. And this ends up saving our runtime by preventing us from making duplicate recursive calls that end up doing the same thing over and over again. So now let's look at the handwritten problem for this week. Your goal this week is to implement a DP solution to the 0-1 knapsack problem, which you should have covered in lecture. So the idea here is that you're given a bag or knapsack of a certain weight capacity cap, and you are given a selection of n items that you can choose from, where each of these n items has a weight and a value. The weights and the values are given to you in vectors, where the ith item has a value located at index I of the value vector, and a weight located at index I of the weight vector. You want to write a program that can essentially determine the maximum value you can attain using your knapsack with the given capacity by filling up the bag with items from the selection without going over your weight capacity. And whatever this best value is, you'll have to return it in your function. So just as a hint, this is very similar to the subset sum problem that we've covered before. Try to think of how you can use dynamic programming and first generate a recurrence relation. That is, how can you use the solution for a smaller input size to help you determine the solution for the larger input size. That is, write the solution for the larger input size in terms of solutions using smaller input sizes. After you do this, then it just becomes turning that recurrence relation into a dynamic programming format. If you use top-down, simply write the solution as you would usually do with the recursive calls that you made based on the recurrence relation that you discovered. But before a recursive call, make sure you check to see if you've seen that value already in a memo. If you use the bottom-up approach, then you initialize a memo like before, but instead you start the base case and essentially fill up your memo all the way up to your input size using smaller input size values to help you solve the values for larger input sizes. So this is it. This is the last lab of 281, the last handwritten problem, and the last lab assignment you'll have to do for this class. Please take the time over the next few days to practice your dynamic programming skills, because dynamic programming will be on the final exam. That's a guarantee in life. One of the written questions will be a dynamic programming question. So I would recommend practicing this as much as you can. Dynamic programming isn't obvious at first. It takes practice to wrap your head around. So practice does make perfect for this type of problem, and being able to go through many different questions will better prepare you when the actual dynamic programming question you have shows up when you take the final exam. One good resource that I do want to recommend is try to look up dynamic programming patterns on Google. Now there's an article, I think it's the first one, but basically on LeetCode, dynamic programming patterns, on LeetCode there is an article that basically kind of goes through different types of dynamic programming questions that you're likely to see, and actually puts them into categories, where each category essentially has the same template that you can use to solve the problem. The hardest part of dynamic programming is generating the recurrence relation. That is how you can build a larger input size solution using the solutions for smaller input sizes. But after you realize what the recurrence relation is, all that you have to do is essentially use a top-down or bottom-up approach to remember the recursive calls that you make so that you can use them later in case you see them again. So this is it. This is the last lab. I would like to thank all of you for putting up with us as we've tried to convert everything to online format. I know a lot of things such as labs and office hours, are a lot more challenging without that face-to-face communication. And I do want to thank all of you for endeavoring through it, and I hope you've made the most out of this class, even with the situation that we're currently going through. So stay safe, good luck on Project 4, good luck on the exam, and I wish you all the very best in this class and any future classes that you take here at the university.